All right, this is AP BC Calculus. We're doing a BC only unit. This is Unit 10, Section 11. We're going to talk about finding Taylor polynomial approximations of functions. So basically this is going to be the video where we learn how to build a Taylor series. Later on we're going to memorize some Taylor series that you should know. So recall that polynomials are the well-adjusted, happy-go-lucky children of the function world. They're easy to integrate, they're easy to differentiate, and often easy to solve. They have very predictable behaviors, right? They have end behavior we can predict. They're easy to find extrema for, all of this nice stuff. So it can be incredibly beneficial to model a more complicated function with a polynomial, right? So enter the Taylor polynomial and the Taylor series. You can create a polynomial with infinite terms, hence a series, centered around a point, which we're going to call x equals a, that will align to your ugly complicated function for x values reasonably close to x equals a. And we're going to call that window close to x equals a. We're going to call that the interval of convergence or just the radius of convergence if you're talking about how far away from a you can get. So the interval would be some portion of space on either side of a, but the radius would just be the distance from a to the edge. So we're going to spend more time on interval of convergence and radius of convergence in 1013. So how do we build this mythical, amazing Taylor polynomial for some function f of x? All right, so to build a Taylor series from scratch for a function f of x, this is the formula we use. We're going to start an infinite sum starting at n is 0. We're going to use the nth derivative of the function evaluated at some center, x equals a, over n factorial times x minus a raised to the n. So what that ends up looking like is the first term is just the 0th derivative would mean don't derive at all, right? So just the function evaluated at a. The reason it just looks like this is an f of a over a 0 factorial, which is a 1, right, times an x minus a to the 0, which is also a 1, which is why it just ends up being f of a. The next term is the first derivative over a 1 factorial, but again, 1 factorial is just 1, so we don't bother, and then x minus a to the first. The next term is the second derivative evaluated at a over 2 factorial, x minus a to the second, and so on. All right, so that's a Taylor series, and it's infinite, right? A Taylor polynomial, right, the nth degree Taylor polynomial just means instead of going to infinity, you only go up to n. And we can denote it as p sub n, or sometimes q sub n if you've already used p for a function. So if you're using, let's say, p sub 1, p sub 2, p sub 3 to approximate some function f of x, and you're asked to approximate a different function, like g of x, you shouldn't use p's for g in the same problem. If you were using p sub 2 to approximate f, then it's q sub 2 to approximate g or something else, but that's the idea. So it's the same concept. We set it up the same way, except instead of going to infinity, we stop at whatever term n is. So the first degree Taylor polynomial, right, p sub 1 for x would be for f of x rather, would be f of a plus f prime of a times the quantity x minus a. The second degree Taylor polynomial, p sub 2 of x, would be f of a plus the next term is f prime of a times x minus a, and the next term is f double prime of a over 2 factorial times x minus a squared. Note that Taylor polynomials approximate the value of a function for given values of x close to a. They're not equal to the actual function, they approximate the function. But if you go back a step, this is actually equal, right? Like the infinite series actually is equal to the function on the interval of convergence, and we'll talk more about that in 1013. All right, so moving on. In example 1, we're going to go ahead and make the second, fourth, and sixth degree Taylor polynomials for f of x equals cosine x, centered at x equals 0. This is actually a series that you're eventually going to memorize, and if some of you have read ahead, you might already know this, but we're going to do it the hard way, right? So my f of x is cosine of x. My f prime of x is going to be negative sine of x. My f double prime of x is going to be negative cosine of x. My f triple prime of x is going to be regular sine. My fourth derivative of x is going to be cosine. We'll just extend this page down a sec. I'm going to go up to 6 because I know that for a, b, c, and d, I'm going to have to go as far as 6 eventually anyway, so I'm just going to go ahead and do it. The fifth derivative would be the derivative of cosine, which is negative sine. And then last one, the sixth derivative would be the derivative of negative sine, which is negative cosine. Okay, so I'm just putting in the work for a, b, and c. You wouldn't actually be asked to do a, b, and c on an AP. You'd only be asked to do one of them in all likelihood. So x equals 0 is my center, so I'm going to find f of 0, and that's a 1, right? F prime of 0, sine of 0 is a 0. F double prime of 0, cosine of 0 is a 1, so this is a -1. F triple prime of 0 is, again, a sine of 0, which is 0. The fourth derivative of this thing at 0 is cosine of 0, which is 1. The fifth derivative is another sine of 0, right? It's got a negative in front, but that doesn't matter, so it's a 0. And then the sixth derivative is another -1 again. All right, and again, we are going to learn a shortcut for this, but for right now, we would need all those derivatives. So if I want to go ahead and answer my A, B, and C, right? So A asked me to find the second degree Taylor polynomial. Well, that's going to be, so we'll call it P sub 2 of x, right? That's going to be F of 0 plus F prime of 0 times x minus 0 plus F double prime of 0 over 2 factorial times x minus 0 quantity squared. So we can clean that up, right? We don't clean it up much, right? I'm just going to plug in the values. So that's a 1 plus this whole second term gets knocked out, the f prime term, right? And then this will be a -1 over 2 factorial times an x squared. So I'm probably going to write my answer to A, and we'll just write it up here actually. Probably write my answer to A as P sub 2 of x equals 1 minus, and if you want to clean up the 2 factorial into a 2, you certainly can, but it's a 1 minus an x squared. Sorry, 1 minus a 1/2 x squared. All right, so if I did B, right, so for B, it's the same start, right? I'm just going to have to do the first 4. I have to go up to x to the 4th, right? So I'm going to recognize that P sub 4 is actually going to start out the same way. It's going to have these same 3 terms. So it's going to start out the same way that I just had this, right? But then I have to do the next term. So after squared would be the third term, right? So it would be F triple prime of 0 over 3 factorial times an x minus 0 cubed, right? Plus the fourth derivative of f at 0 over a 4 factorial times an x minus 0 to the 4th. So if you notice, the third derivative, right, f triple prime was a 0, right? So to keep going with B, I have P sub 4 equals a 1 minus this 1/2, or a 1 over 2 factorial if you want. This thing zeroes out, right? And then I'm going to get plus a 1 over 4 factorial and then x to the 4th, right? Because there's x minus 0 to the 4th. If you want to clean up 4 factorial, you certainly can. You don't have to, right? So P sub 4 of x, right? P sub 4 of x would be 1 minus 1/2 x squared plus, and you could either leave it as a 1 over 4 factorial or you could make it a 1/24. It doesn't really matter, x to the 4th, right? Either of those would be fine. To get to the 6th degree polynomial, I'm just going to cheat and use all that work I just did, right? I'm going to add 2 more to it. So for the 6th degree polynomial, P sub 6 of x, I already know what the first several are going to come out to be like, right? This got me up to the 4th. I just need to do the last couple terms. So I'm going to get the 5th derivative evaluated at 0 over a 5 factorial times an x minus 0 to the 5th plus the 6th derivative evaluated at 0 over a 6 factorial times an x minus 0 to the 6th. So seems to me that my P sub 6 of x is going to be a 1 minus a 1/2 x squared plus, and again, if you want to leave it as a 4 factorial, that's totally fine. This zeroes out because we can see up here that the 5th derivative would be evaluated at 0 would give me a 0. And this seems to be a -1, so -1 over 6 factorial x to the 6th. Again, this answer is totally fine if you like it. If you'd rather leave this as numbers, if you want to not leave it as a factorial, if you want to do 1/2 x squared plus 1 over 24 x to the 4th minus, my bad, I made a plus, minus 1 over 720 x to the 6th, that's totally fine. That's also fine. So the next thing I asked you to do is I asked you to graph in your calculator the original function. So we're going to go to y equals, and we're going to put in the original function, which is cosine x, right? We're going to put in P sub 2, which was a 1 minus a 0.5 x squared, right? We're going to put in, so I'm not going to graph all of them at once. I'm going to do it one at a time, but I am going to put them, I'll put them all in and then I'll just turn them on one at a time. I want to show you that as you use infinite terms, that your approximation with this polynomial is going to get better and better. So as we add, oops, sorry, that's a 24. As we add terms to our approximation, you're going to see that the approximation matches better and better. And so let me do the last one, which would be 1 minus 0.5x squared plus 1/24 x to the 4th minus, and you could do 1/6 factorial. You certainly don't have to type it in as a 1/720 x to the 6th. All right, so I'm gonna go ahead and I'm gonna do a couple things, right? So the first thing I'm gonna do is I'm gonna change this to the thick line, and then I'm gonna turn it off for a sec, and I'm gonna do that with each one of them. I'm gonna change it to the thicker line, and then I'll turn it off. Okay. So I want to graph the least accurate of these first. So the cosine is going to graph with the least accurate approximation, which is the second degree Taylor polynomial. So watch what happens. There's cosine, and see how in this window, right? So right here, if we zoom in, so let's zoom in a little bit, you're going to see that that function really closely aligns, right? Like that parabola that we have very closely aligns to cosine, right? Okay, so that was not a bad alignment. Now let's turn that one off and get a little more accurate by making it the 4th degree Taylor polynomial. Now watch what happens. I'm going to zoom 6 again so you can see it a little better. So zoom 6. Oh, well now this aligns even better, because remember where the polynomial that we had at the beginning, where the quadratic only aligned for sort of this window to this window, this thing aligns all the way down to here and here. That's even better, right? So then let's go ahead and turn off the 4th degree, right? And then we'll zoom 6, and what you're going to see is this matches even better. Look at that. Look how well that matches, right? Like this crazy x to the 6th graph matches this really, really well. And you can see, again, if we zoom in a little bit, you'll see that they basically are the same graph on the entire window I can see, and I could actually make this go to, let's say, -5. And 5, and maybe that'll show us a little bit better where that split happens. But look how closely that matches, right? That's almost a perfect graph. So this polynomial is doing an exceptional job of standing in the place of cosine of x, right? So that's the idea of Taylor polynomials. They're used to approximate functions. Now, certainly you might say, well, you know, Hogan cosine isn't really a particularly ugly function, and you're right, it's not. Cosine's one of the friendlier functions, but that's what we're using Taylor polynomials for. We're using them to approximate curvy, crazy functions with nice, happy polynomials. All right. You're going to go ahead and try a P1 that's basically the exact same thing. And again, we are going to memorize the series for sine of x. So just to be clear, I could have given you all 3 of these, P2, 4, and 6, from memory with almost no work. Well, I mean, basically no work, just memory, right? And hopefully we're going to get to that point too, but I'm using these as examples because they're fairly friendly examples. So let's walk through P1 where we're going to do the same thing, right? You're going to find the 1st, 3rd, and 5th degree polynomials, so P sub 1, P sub 3, and P sub 5, right? For f of x is sine x, right? So my f of x is sine, right? My f prime of x would be cosine. Right, f double prime of x would be negative sine. F triple prime of x would be negative cosine. The 4th derivative would be regular sine, right? And the 5th derivative, which is how high I need to go because this said go up to the 5th degree polynomial, well, that would be a cosine, right? So, so if I wanted f of 0, because I am going to have to plug in the actual values, right? Sine of 0 is 0. Cosine of 0 is 1, sine of 0 is 0, cosine of 0 is a 1, and there's a negative in front of this one, so that's a -1. Sine of 0 is 0, and cosine of 0 is a 1, right? So when I go to find these polynomials, right, so when I go to do A, let's say, right, P sub 1 of x is going to be f of 0 plus f prime of 0 times x minus a. And if you don't want to write x minus 0 because in your brain you say, wait a second, it's just an x, that's fine because it's a 0, I get it. This is going to be 0 plus a 1 times an x. And that's it. So my P sub 1 of x is really just an x. When I go to do B, my P sub 3 of x is going to be f of 0 plus f prime of 0 times x minus 0 plus f double prime of 0 over 2 factorial times x minus 0 squared plus f triple prime of 0 over 3 factorial times x minus 0 quantity cubed. Well, I'm going to clean that up using the values that we have over here, and that P sub 3 of x seems to be a 0 plus an x plus a 0 minus, because this would be a -1, so -1 over 3 factorial x cubed. So it seems to me like my p sub 3 of x is an x minus, and you can leave it as a 1 over 3 factorial x cubed, right? Or you could write it, there's other ways you could write it. You could write this as x, minus, right? You could write this as x minus x cubed over 3 factorial, which is probably the most common option, right? Or you could write this as x minus an x cubed over 6, because that's what 3 factorial is. Any of those would be fine. And then lastly, my p sub 5, right, which I'm going to cheat and just spoil what this is. It's x minus this x cubed over 3 factorial plus it'll be an x to the 5th over 5 factorial, and we're going to walk through that in just a sec. So to find my last one, my p sub 5, right, I'm basically going to use all the stuff I already have, right? We already used the first 3 terms, so I'm going to have this x minus this x cubed over 3 factorial, right? And then I'm going to need the 4th term, because this only goes up to the 3rd derivative, right? So I'm going to need the 4th derivative at 0 over 4 factorial times x minus 0 to the 4th, plus the 5th derivative at 0 over 5 factorial times an x minus 0 to the 5th. Well, as we can see right here, the 4th derivative is a 0, right? So this thing zeroes out. So I get that my p sub 5 of x is an x minus this x cubed over 3 factorial, and then this 5th derivative evaluated at 0 is a 1, so plus a 1 over 5 factorial, or you can just make that an x to the 5th on the top. You can either put the x to the 5th after or put it on the top. So there's my 5th degree polynomial. And then I asked you to do the same thing, right? I said, hey, since you're here, graph all 3 and see what happens, right? So let's go ahead and change this to a sine, right? We're going to change this to just an x. We're going to change this to an x minus x to the 3rd divided by, oh, and if you want, you can do 3 factorial. You can do 3, go to math, over to probability, and 4. You can actually make it do 3 factorial for you. Or you could make it a 6. I don't really care. And then you can do the same thing here. You can make this x minus this x to the 3rd divided by 3, math over to probability and pick 4, right? Plus, and then you could do an x to the 5th divided by, in parentheses, 5 math over to probability and pick 4. And you could delete. Okay, so if we do the same thing, notice, so what I'm going to do is I'm going to turn off the better 2 approximations and start with the worst of the 3. I'm going to zoom 6, and you'll see that right in this window, if I zoom in a little, right, right in this window, that line does a pretty good job of approximating sine, right? But if I do it with the next one, like that only approximates sine for sort of the interval right around 0, right? So if I do it again, well, hey, that looks really good, right? That's a pretty good approximation. That thicker curve is a pretty good approximation. And if I want to get even closer, well, now that looks almost perfect, right? There's a little bit of a split here, but that's pretty darn perfect. And I can zoom 6 to show you that it's not perfect forever. It's only perfect around that window. But interestingly enough, if I use the infinite Taylor series, if instead of having 3 terms or 5 terms or 7 terms or 20 terms, if I pick something that has infinite terms, then it actually is this curve. It would be a sine or a cosine curve, which is kind of cool. All right, so we're going to go ahead and compute a 2nd degree Taylor polynomial for this thing, centered at 0, and then we're going to use that to approximate f of 0.1. Okay, so to find a 2nd degree Taylor polynomial, so my p sub 2 of x should be f of 0 plus f prime of 0 over 1 factorial, so you don't have to write that if you don't want, and then x minus 0 to the 1st, right, plus f double prime of 0 over 2 factorial, and then an x minus 0 to the 2nd. So basically, I need 3 things. I need this, and this to write my Taylor polynomial. That's what I need. So f of 0 is easy, right? F of 0 is e to the tangent of 0, which is e to the 0, which is 1. So that's a 1. Great. I need f prime of 0. Well, that's going to involve finding f prime. So f prime of x is going to be the derivative. So derivative of e to the stuff is e to the stuff times the derivative of the stuff. So f prime of 0 is going to be e to the 0 times, so secant squared, right? Secant is 1 over the cosine right? So it's a 1. So I'm going to get 1 times a 1 squared, which is just a 1. So that's also apparently a 1. Okay, that's a 1 also. And then to find the last missing piece, right, f double prime of 0, I need to find the second derivative. So that's going to be less fun. So f double prime of x is going to use a product rule, right? So here's my u and here's my v. So u dv is less fun. It's going to be the derivative of secant squared, which is 2 secant to the first times the derivative of secant. Okay, so this was my u, this was my dv, plus v, which is secant squared, du, which is e to the stuff times the derivative of the stuff. All right, so that was a lot of fun. So this is my v du. That's good times. I was being slightly sarcastic there. I need f double prime of 0. Well, that's going to be an e to the 0 times a 2 times a 1 times a 1 times a 0. Well, that's nice. That whole one's going to get knocked out. And then this is a 1 times an e to the 0 times another 1. So it seems like I get 0 plus 1. So I just get another 1. Now, that's not always going to happen, but it turns out that this guy is also a 1. So when I write my Taylor polynomial, sorry, we just need to extend our page a little bit. So my p sub 2 of x is going to be 1 plus 1 times an x plus a 1 over 2 factorial, which is just a 2, x squared. So that's my Taylor polynomial. Okay, so that's the first thing I was asked to do. I'm then asked to use that, so I'm going to use p sub 2 of 0.1, right, to approximate f of 0.1. Well, p sub 2 of 0.1 is equal to 1 plus 1 times 0.1 plus a half times a 0.1 squared. And you might be thinking, hey, this is awful. How would I do this without a calculator? It's actually not bad if you recognize that 0.1 is a tenth, right? So this is 1/10, and this is a 1/10 squared, which just makes it a hundredth, right? So this is a 1 plus a 0.1 plus, this is a half of a hundredth, which would look like this, right? So half of a hundredth, there's a couple ways to think about this, right, if you don't have a calculator. So half of a hundredth, if you think about this as 0.0110, right, half of that would be 0.005 because half of that 10 would be 5. Another way to think about it is if you do 1/100th times 1/2, you get 1/200th, which is the same as 5 over 1,000, right, if you times by 5. So I'm going to get that this is a 1 plus a 0.1 plus a 0.005, which means I get 1.105. F of 0.1 is approximately 1.105. And that's a level of decimal math you can be expected to do on an AP without a calculator. But notice that this is a question that gives you 2 prompts, right? It says, hey, write the second degree Taylor polynomial, then use it, right? And that's kind of the gist. All right, so you're going to go ahead and give that a try on P2. Same thing, we're going to do a second degree Taylor polynomial, and then we're going to use 0.5s because I thought that those weren't awful to have to square or multiply and such. All right, so I know that my p sub 2 of x should be f of 0 plus f prime of 0 times x minus 0, which is just an x, right? Plus f double prime of 0 over 2 factorial times an x minus 0 squared, so just an x squared. So again, I really need to find 3 things. I need to start by finding f of 0. Well, f of 0 is going to be e to the 2 times the sine of 0, which is just e to the 0 again, so hey, that's a 1. Great. I need to find f prime of 0, which is going to involve differentiating first, right? So f prime of x is going to be e to the stuff times the derivative of the stuff, right? So when I plug in, sorry, I shouldn't have put an equal there because it's not equal. So now when I find f prime of 0, which is not the same as f prime of x, I'm going to get e to the 0 times 2 cosine 0, which is a 1 times a 2 times a 1. So it's just a 2. So this guy's a 2. Right, so we know 2 of our, oh, sorry, wrong color. We know 2 of our coefficients that we need. There we go. All right, cool. All right, and then last one, we need to find f double prime of 0, which again is going to involve finding f prime or f double prime, and that's going to be another product rule, right? So I have my u and my v, right? So my f double prime of x is going to be u dv, well, the derivative of 2 cosine of x is a negative 2 sine of x. That's fine, right? plus v, which is 2 cosine of x, du, right, which is going to be, the derivative of u is going to be e to the stuff times the derivative of the stuff. So when I plug in for f double prime of 0, I'm going to get e to the 0 times a bunch of zeros, so that's gone, plus this is a 2 times a 1 times an e to the 0 times a 2 times a 1. So I'm pretty sure I get 2 times 1 times 1 times 2 times 1, which is just a 4. So I get a 4 for this thing. Okay, so now let's go ahead and see what happens. That means that my p sub 2 of x is going to be f of 0, which was 1, plus f prime of 0, which was 2, x to the first, plus f double prime of 0, which is 4, over 2 factorial times an x squared. So it seems to me that I get that p sub 2 of x is a 1 plus a 2x plus a 2x squared. So that's the approximation that you want. That's the second degree Taylor polynomial. We're then going to use that approximation to approximate f of 0.5, I believe. Yep, okay. So f of 0.5 is approximately p sub 2 of 0.5, which is going to be a 1 plus a 2 times a 0.5 plus a 2 times a 0.5 squared. So that's a 1 plus a 1 plus double of a 0.25, because that's what squaring a half gives you a fourth, right? So I seem to get 1 plus 1 plus 0.5. So f of 0.5 is approximately 2.5. That's all. All right. So sometimes we're given a situation where we're not actually given the equation and we don't know anything about the equation, which can seem really daunting but is actually easier. Because if you go back to the last couple examples, you can see how like these slides have a lot of work. But if you look at what the bulk of the work was, the bulk of the work was finding these colorful things that I circled here. What is this? What is this? What is this? That was a ton of work. The same thing happened in the next example. What was the red thing? What was the blue thing? What was the green thing? That took a ton of work. Well, look, here you're being handed that information. You're being given g of 5, g prime of 5, g double prime. That's it. They just want you to write the polynomial. So what is the Taylor polynomial of degree 3 for g centered at 5? Now this is the first one we've seen where the center wasn't 0, but it's not a big deal. So p sub 3 of x is going to be g of 5 plus g prime of 5 times x minus 5 to the first plus g double prime of 5 over 2 factorial times an x minus 5 to the second, and then the last one, g triple prime of 5 over 3 factorial times an x minus 5 to the third, right? That's it. So I just need to plug the numbers in. So my answer to A, even though this looks daunting, I'm actually in a much better situation. All the parts that took a ton of work in the other examples are done for me here. G of 5 is a 3, right? Plus g prime of 5 is a negative 2 times this x minus 5, right? G double prime of 5 is a 7, so 7 over 2 factorial, or 7 halves, doesn't really matter, and then an x minus 5 quantity squared. And then g triple prime of 5 is a negative 3. So this is going to be a negative 3 over a 6. If you want to leave it as negative 3 over 6, that's fine. Nobody cares, right? You don't have to simplify these things. This is fine. So this is the answer I would give. If you want to clean up any of those fractions, you certainly could. Doesn't matter. I'm then asked to use that approximation or use that value to approximate g of 4.9. So g of 4.9 is approximately p3 of 4.9. So all I have to do is plug in 4.9s. And you might be thinking, oh my gosh, but that's horrible. The thing is, it's really not, because I didn't FOIL out any of this stuff with x minus 5, right? So 4.9 minus 5 is just a negative 0.1. So this is a 3 plus this negative 2 times a negative 0.1, right? Plus a 7 halves or a 3.5, doesn't really matter to me which one you pick. And then a negative 0.1 quantity squared, which we'll talk about in a sec, right? Plus this is a negative 0.5 times this negative 0.1 quantity cubed. So the nice thing about multiplying by tenths is it just means move the decimal place, right? So this is going to be a 3, and then because it's a negative times a negative, it's going to be a 0.2, right? This is going to be a 0.01. That's what happens when you square, right? So this thing is going to be a 0.01. So that means move the decimal place 2 places. So if it's here, it's going to go 1, 2. I'm going to get a 0.035, right? This one's going to come out to be a negative 0.001, which just means move the decimal 3 places. So 1, 2, 3. So this is going to end up being a plus because there was a minus and another minus. 0, 0, 0, 5. And you might think, oh, that's horrible, but really it's not, because you're just adding decimals straight down, right? If you line them up, if it helps you, you can do this, right? This is a 0.2, and this is a 0.035, and this is a 0.0005, right? If you add straight down, this is a 5, this is a 5, this is a 3, this is a 2, and that's a 3, and there you have it, right? So your g of 4.9 is approximately this value. And that's it. All right, so let's try a P3, same idea. It looks daunting, but again, you're handed a bunch of this information, right? So you're going to write the second degree Taylor polynomial of h centered at -2. All right, so first thing I'd do if I were you is I'd write what the second degree Taylor polynomial should include, right? So that's h of -2 plus h prime of -2 times x minus a -2, which you're probably going to write as +2. Plus h double prime of -2 over 2 factorial times an x plus 2 quantity squared. That's what I want, and then it's just my job to look for those things. Well, I'm given h of -2, right? I'm given h prime of -2, and I'm given h double prime of -2. So again, most of the work that you had to do in the other examples, you just don't have to do here. You're just looking it up, right? So this is a 3 plus a -4 times the quantity x plus 2. Plus a 6 over 2. Again, you can leave it as a 6 over 2 if you want. It doesn't matter. Times an x plus 2 quantity squared. So that's my part A. Again, if you want to simplify 6 over 2, you certainly can, but that's not a requirement, right? Then I'm going to use it to approximate -2.1. So, so for part B, right, h of -2.1 should be approximately P2 of -2.1. So I'm just going to plug in and get, that's a 3 plus this -4 times a -0.1, right? Plus a 3 times, this -0.1 is going to be squared, right? So what's going to happen here, right? This means move one decimal place. It's worth noting that a -0.1 is actually a 0.01, right? It's 1/100th. So I'm going to get that this is a 3 plus a 0.4, because the negative times the negative makes positive, right? And then this is going to move 2 decimal places, so this is going to be a 0.03. So I get that h of -2.1 is approximately a 3.43. And you can't add extra places because that's how many places you know, right? You're not able to tack on more information. All right, moving on. Okay, so now this is the same idea, but a little bit in reverse. And I'm trying to throw you a lot of these questions so you can see the different ways you could be asked about a Taylor polynomial. So in this case, you are given the Taylor polynomial, and you're asked to reverse engineer what are the values of f, f prime, f double prime, f triple prime. Okay, so here's the trick. We know what the definition of p sub 3 of x should be. It should be f of 0, right, plus f prime of 0 over 1 factorial, if you want to write it, and then an x minus 0, right, plus f double prime of 0 over 2 factorial times an x quantity squared, because it'd be x minus 0 squared, right, plus my f triple prime of 0 over 3 factorial times this x minus 0 cubed, okay? So now I want you to look at what we know the polynomial should be and compare it to what we're given, right? We were given that p sub 3 of x is a -3, which is the constant term. There's nothing here. There's no x term, right? Plus a 7x squared, that would align with the x squared term, minus a 2x to the third. So here's what we can infer from that information. This has to be my f of 0. Right? F of 0 must be a -3. That one's done. The next thing I can infer is that since there's nothing here, that must be a 0, right? Well, that means that f prime of 0 must be a 0 because there is no term there. 1 can't be 0. X is just an x. Since there are no x's, that must be a 0. Similarly, this 7 has to equal this whole mess. So f double prime of 0 over a 2 must be 7. That must mean that f double prime of 0 is a 14. Right? And then the last one, because I'm kind of out of space, but I'll manage to squeeze this in, right? For the last one, these two things also have to be equal, right? So f triple prime of 0 over a 6, because that's what 3 factorial is, has to equal a -2. It must mean that f triple prime of 0 is a -12, right? So again, I'm using the definition of what the Taylor series is, what a Taylor polynomial is made up of, and I'm comparing what's given to that value. All right, so now that I have those, the next question I was asked is, does f have a local max, min, or neither at x equals 0? Well, this is probably asking me about the second derivative test. The reason I say that is I have the second derivative at 0. Second derivative, I can't handle writing. I don't know, guys, my brain broke. Second derivative test, we're just going to go with that because my brain broke. So we know that f prime of 0 is 0 because we just found that in green right here, right? We said so what that means is that the function is flat. We also know, we found in black right here, that f double prime is a 14, right? So f double prime of 0 is a 14, which means my graph is concave up. So f of x is concave up at x equals 2, or sorry, x equals 0 rather. Well, that's a min, right? By the second derivative test, that's a minimum, right? Because what's happening is I have a graph that is concave up and also level. That's got to be a min, and that's what they're looking for you to say. So you need to say, hey, these two things are true, this is true, and this is true. So by the second derivative test, it's a minimum. All right, I want you to go ahead and give that a try again, but you're going to do P4, same idea. So here, you're given a fourth degree polynomial centered around x equals 1, and you're asked to find the values of f of 1, f prime of 1, f double prime 1, f triple prime 1, and the fourth derivative of f at 1. And then you're asked whether 1 is a relative max, min, or neither for the function. So again, the best thing you can do here is say, hey, I know what a Taylor polynomial is supposed to look like, right? I know that p sub 4 of x should be f of 1 plus f prime of 1 times an x minus 1 plus f double prime of 1 over a 2 factorial times an x minus 1 squared plus f triple prime of 1 over 3 factorial times an x minus 1 cubed plus the fourth derivative evaluated at 1 over 4 factorial times x minus 1 to the fourth. And then you can line them up. So we'll start with the first one. The 7 has to be this guy, right? That's a 7. So f of 1 is a 7, right? Not really a lot of work there, okay? For the next one, I think that's a negative. I kind of wrote on top of it. Let me fix it. So the negative 3 has to be this coefficient, right? Like this has to be the negative 3 in front of, oh, sorry, I take it back. Clever, clever, clever. There is no linear term. So there's no x, right? Which means that this guy must be 0. Because there is no x term, then let's go to the green. This guy's the coefficient of the x squared. Well, here's your x squared term, so this thing has to line up with a negative 3. So what we can say is that f double prime of 1 over 2, because that's what 2 factorial is, right, equals a negative 3. So f double prime of 1 must be a negative 6, right? In purple, this is the coefficient of the cubed term. Well, this is the coefficient of the cubed term. So f triple prime of 1 over a 6, because that's what 3 factorial is, right, equals a 5. So f triple prime of 1 must be a 30, right? I'd multiply the 6 over. And then let's loop back to red. This is a negative 1, right? And that has to align with this value. So we'll squeeze this one up here. The fourth derivative evaluated at 1 over a 4 factorial, which is a 24, right? 4 times 3 times 2 times 1 should be a negative 1. So I think I get that the fourth derivative at 1 is a negative 24. Okay, so that's my answer to the first part, right? So these guys right here, so this and this. This is my answer to the first question, right? What are those values, right? The second question is, again, going to be about the second derivative test, right? So we know that f prime of 1 is 0. We also know that f double prime of 1 is a negative 6, which is less than 0. So we're looking at a graph that is concave down and level. That's a max, right? So f of 1 is a max by the second derivative test. So this is really taking you back pretty far. This is taking you back to maybe Unit 3 of AB, right? It's been a while, remembering how these tests work, but it's a great application of a Taylor polynomial. All right, so again, we've seen different examples, ones where we had to build a Taylor polynomial from scratch, one where we were given information, one where we have to reverse engineer information from a Taylor polynomial. All right, A function g of x satisfies the differential equation g prime of x equals g of x plus x squared plus 4. And we're given that g of 0 is -7. We're going to write a second degree Taylor polynomial about g of x for x is 0. Okay, so again, the first thing you want to do is say, hey, if I'm asked to write a second degree Taylor polynomial, what would that entail? Well, this is for g of x about 0. So it's going to be g of 0 plus g prime of 0 times x minus 0 plus g double prime of 0 over 2 factorial times an x squared. Once you know that, you realize that you just need to find these values. Well, I already know g of 0, it was given. So this is a -7, that's great, right? I can find g prime of 0 because I was given a formula for g prime, right? So g prime of 0 should be g of 0 plus 0 squared plus 4, which is a -7 plus 0 plus 4, or a -3. So I now have a number for g prime of 0. The trickiest one to find is going to be g double prime of 0, right? Because I'm going to have to differentiate, right? So to find g double prime of 0, I'm going to have to start with g prime of x rather, equals g of x plus x squared plus 4, and I'm going to differentiate. So g double prime of x is going to be g prime of x plus 2x. Once I know that, g double prime of 0 is just g prime of 0 plus 2 times 0, which means that I get that g double prime of 0 is just a -3. So now I can go ahead and write my Taylor polynomial. So p sub 2 of x equals -7 minus a 3 times x, and then this is going to be a -3 over 2 x squared, right? So there's my second degree Taylor polynomial. Next, use your second degree Taylor polynomial to approximate g of 0.5. So now we're going to plug in 0.5. So, this was answer A, right? Answer B, g of 0.5 is approximately p sub 2 of 0.5, right? Which is going to be a -7 minus a 3 times 0.5, which we'll deal with in a sec, minus a 3/2 times this 0.5 squared, right? I think it was just a regular 0.5. Yeah. Okay. So this is a -7, right? It's up to you whether you want to make this a 3/2. Like, there's an argument for either case, whether you're a decimal person or a fraction person. I'm a bit more of a fraction person, especially when I have 3/2 times a fourth, right? Because that's what a half squared would be, is a fourth. So for me personally, I'm probably turning everybody into a fraction, but it's up to you. It doesn't really matter. The common denominator is definitely going to be an 8, right? So I could make this 56 over 8, right? And then this would end up being a 12 over 8, right? Because I'd multiply by 4 over 4 and then minus a 3 over 8. So I end up getting that that's a -71 over 8. If you were somebody that would prefer to write it as a decimal, you definitely could. I just think it depends on the person, whether that's easier for you or harder for you. It just depends on you as a person. So, all right, go ahead and try a P5 that's the same basic idea. Again, you're given a differential equation that defines f prime in terms of f, and we're going to write the second degree Taylor polynomial. So again, the very first thing you should do here is say, hey, what does a Taylor polynomial of the second degree require? Like, what do I need, right? And we're doing this about about x is 1, right? So this is going to be f of 1, right, plus f prime of 1 times an x minus 1, right, plus f double prime of 1 over a 2 factorial times an x minus 1 squared, right? So what you need f of 1, but that's given. So hey, that's a 3, great. You need f prime of 1. Well, we have a formula for f prime. So f prime of 1 is going to be 2 times f of 1 plus a 3 minus a 1, right? So that's going to be a 2 times a 3 plus a 3 minus a 1. That's 6, right? Plus 3, which is 9, minus 1, which is 8. So we now know that this thing's an 8. Okay. And then for the last one, we are going to have to differentiate, right, to find this thing. I'm going to need to find that f double prime of x, if I differentiate f prime, I get f double prime, equals 2f prime of x plus a 3. So my f double prime of 1 should be a 2 times f prime of 1 plus a 3, which seems to be 2 times 8 plus a 3, or a 19. So now that I have all those values, my answer is going to be that p sub 2 of x is a 3 plus an 8 times an x minus 1 plus a 19 halves times an x minus 1 quantity squared. So I'm approximating, so that was my part A, sorry, part A. My part B is that I'm going to approximate f of 1.1 by using that p sub 2 of 1.1, right? And again, tenths are sort of the most friendly thing you can plug in, because when you get a difference of 1/10, it's just going to move the decimal place, which is lovely. It's about the nicest that it can get. So when I plug in, I'm going to get that this is approximately 3 plus an 8 times a 0.1, which will just be a 0.8, right? Plus, and admittedly, 19 halves is less fun, right? So that's a 9.5, right? Times, this is going to be a 0.01, because it's going to be a negative 0.1 quantity squared, but if you square a tenth, you get a hundredth, right? So basically, this is going to be a 3 plus a 0.8 plus, and then the decimal place gets moved twice. So so once twice would be 0.095, right? So I'm going to end up getting that this is approximately a 3.895, and that's my f of 1.1. All right, moving on. I know this has been a long video. All right, so same situation. You look at this and you start to panic, and you think, oh no, I don't know what to do. This is horrible, right? Selected values of g of x and its derivatives are given below. Notice that all of these derivatives are given at x equals 2, right? So this is g of 2, which is g prime of 2. This is just a clever way to try and trick you. Write a third-degree Taylor polynomial for g of x about x equals 2. Well, first thing you have to ask yourself is, what would that require? Well, it would require g of 2 plus g prime of 2 times an x minus 2, right? Plus g double prime of 2 over a 2 factorial times an x minus 2 squared, plus a g triple prime of 2 over 3 factorial times an x minus 2 cubed. Once you realize that, all of this information is present on the table. This is g of 2, right? Because it says when x is 2, right? So g of 2, definitely a 5. G prime of 2, definitely a 3. G double prime of 2, definitely a 6, right? And then G triple prime of 2, definitely a negative 24. And I don't need the fourth derivative, right? Sometimes they just give you something as a trap. So my p sub 3 of x is going to be a 5 plus a 3 times the quantity x minus 2 plus a 6 over 2. So you can either leave it as 6 over 2 or you could make it a 3, right, times x minus 2 quantity squared, plus a negative 24 over 6. So if you want to leave it as a negative 24 over 6, you totally could, but you could also make it a negative 4, and then it's an x minus 2 cubed. Okay, that's my part A, right? My part B is to use that to approximate g of 1.9, right? So that's going to be a 5 plus a 3 times a. When you do 1.9 minus 2, you get a negative 0.1, and yet again, you're going to see that nice same happy thing where we're talking about 0.1s, and that's great because it's just about moving a decimal place. All right, so let's clean this up a little. This is a 5, a negative 0.3. This is a plus, and then this is going to be this is a 0, 1, right? So it's moved the decimal place 2 places. And this is going to be a 0, 0, 1, but it's going to stay negative because it's to the third. So this is going to be plus a 0.004, right? So it's up to you how you want to deal with this, right? I would probably say, since this guy's the only negative, right? Again, totally up to you. I might deal with this first, right? I might say, hey, this is a 4.700, right? Like, because that's what, if you subtract 5 minus 0.3, you get 4.7, plus this thing, and then that's pretty straightforward. So I'm going to end up getting this is a 4.734. That's my g of 1.9, right? You do want to get a little bit comfortable with working with decimals just because it does come up. All right. Let's do the same thing, right? Again, it looks daunting, but it's not meant to be daunting, right? So you have to ask yourself, what does the prompt ask me to do? Third degree Taylor polynomial for f about 8 should be f of 8 plus f prime of 8 times an x minus 8 plus f double prime of 8 over 2 factorial times an x minus 8 squared plus f triple prime of 8 over 3 factorial times an x minus 8 cubed. Once you know that's what you need, it's your job to go back and look for that information. Well, here's f of 8, so that's a negative 7, right? Here's f prime of 8, so that's a 2, right? Here's my f double prime of 8, so that's going to be a negative 10, right? And here's my f triple prime of 8, so that's going to be an 18. So I end up getting that my p sub 3 of x is a negative 7 plus a 2 times x minus 8. This will be a negative 10 over 2, so minus 5 times an x minus 8 quantity squared. And then this will be an 18 over 6, so that'll be plus 3 x minus 8 quantity cubed, right? So that's my answer to A. And then in part B, I'm asked to use that polynomial I made, plugging in 8.1, which yet again gives me that convenient 0.1 thing that you're going to see a lot of. So g of, oh, sorry, it says g, it should have said f. You get the idea. Sorry, my bad. That's a typo. It's f, because everything about this is f, right? So f of 8.1 is approximately negative 7 plus a 2 times a 0.1 minus a 5 times a 0.01, because when you square the 0.1, that's what's going to happen, right? Plus a 3 times the 0.001, because when you cube a 0.1, that's what's going to happen. So I end up getting that this is a negative 7 plus a 0.2 minus a 0.05 plus a 0.003. It's up to you how you handle this. It really doesn't matter to me. I would probably combine the negative stuff first and recognize that this is a negative 7.05, right? And then the positives together are a positive 0.203, right? How you want to add or subtract this is entirely up to you. It's a little bit tricky, right? Basically, the way to do it is do subtraction, right? Do this thing minus this thing, but recognize that it will net negative, right? It's easier to subtract the bigger number minus the smaller number, but recognize that it will net negative. So, so there's a 0 here, right? So if you're doing this without a calculator, you're going to have to borrow from here and make that a 4. So you get a 7. 4 minus 0 is 4. You have to borrow and get an 8, and that's a 6. So you're going to get that your answer is a negative 6.847. All right, moving on. Okay, so we're going to let f of x equal the cube root of x, and we're asked what is the approximation of the cube root of 2 obtained by using the second degree Taylor polynomial for f of x about x equals 1. So we need the second degree Taylor polynomial for f of x about x is 1. The first job you need to do is create that. So p sub 2 of x should be f of 1 plus f prime of 1 times x minus 1 plus f double prime of 1 over 2 factorial times x minus 1 squared. So you need to find this value, which is pretty easy. F of 1 is just the cube root of 1, which is 1. You need to find this value. Well, f prime of x, since this is actually an f of x equals x to the 1/3, right? So this is going to be 1/3 x to the negative 2/3, right? Or it looks like this, right? F prime of x is a 1 over 3 times x to the 2/3. Well, that means that f prime of 1 is a 1 over 3 times 1, or just a 1/3, right? And then for the last one, I'm going to need to find this f double prime. So f double prime of x should be a negative 2/9 x to the negative 5/3. And again, since I'm just plugging in 1 for the power, it's not actually that it's going to matter. Like, plugging in 1 to a power doesn't really matter that it's to the 5/3 because it's going to be a 1. So f double prime of 1 is a negative 2/9. Okay, so now once I know that, I need to write this Taylor polynomial. So I'm going to get that my second degree Taylor polynomial is 1 plus 1/3 times an x minus 1. And then notice this purple thing is a negative 2/9 divided by 2. So that's going to be a negative 1/9 x minus 1 squared. Great. I'm then asked to approximate f of 2, right? Because the square root of, or the cube root of 2. So f of 2, which is the cube root of 2, is approximately 1 plus 1/3 2 minus 1 plus this negative 9th times a 2 minus 1 squared. So it's approximately 1 plus 1/3 minus 1/9. If I get everybody into one nice happy fraction, this is 9/9 plus 3/9 minus 1/9, which is 11/9, or 1.22 repeating, right? That's what 11/9 would come out to be. So the cube root of 2 is approximately 1.22 repeating. And we can actually see what happens if we do that, right? We could do 2 to the 1/3 and see what happens. Oh, hey, that's because that's not a caret. My bad. Sorry. That didn't come out right at all. Hang on, it hates me. There we go. All right, 2. There we, nope, I did press second. Oh, I didn't mean second, that's why. Come on, brain. 1/3. There we go. Hey, not bad, right? So that's our value approximating the cube root of 2. All right, cool. Let's go ahead and do another one. So same idea. All right, so now we have g of x is the square root of x. What is the approximate value of the square root of 8 using the second degree Taylor polynomial about x is 9? Okay, so again, if you're being asked to use the second degree Taylor polynomial about x is 9, the first thing you should do is make that Taylor polynomial, right? So that should be g of 9 plus g prime of 9 times x minus 9 plus g double prime of 9 over 2 factorial times x minus 9 quantity squared. So I now need to find those values, right? Well, g prime of 9 is pretty easy, right? G of 9 is pretty easy, right? G of 9 is just root 9, which is a 3, right? So that's pretty straightforward, right? G prime of 9, right? So to find this guy, I know g of x is x to the 1/2. G prime of x is a 1/2 x to the negative 1/2, or honestly, we probably write it like this, which means that g prime of 9 is a 1 over 2 times 3, or a 1/6. G double prime, right? So G double prime is going to be what happens if I multiply this negative 1/2 down. So I get negative 1/4 x to the negative 3/2, right? So that's a negative 1 over 4. And then it's a square root of x cubed, or can either write it as a square root of x cubed, or the slightly better option to write it if you're doing stuff in your head is the square root of x quantity cubed, right? So G double prime of 9 should be a negative 1 over 4 times, so this would be the square root of 9, which is 3 cubed, so that's a 27, and that's like a pretty ridiculous, crazy number. So should be 108, I think, right? Because it's an 80 and a 28. Yep, so negative 108, so 1 over negative 108, or whatevs. Okay, so it seems that my second degree Taylor polynomial is going to be 3 plus a 1/6 times x minus 9 minus a 1 over 108, which is less fun, x minus 9 quantity squared, right? And I want to approximate the square root of 8, right? So that's my second degree Taylor polynomial. So g of 8, which is the square root of 8, would be approximately 3 plus a 1/6 times a negative 1 minus a 108 times a negative 1 squared. So that seems to be 3 minus 1/6 minus 1 over 108, right? So honestly, that's fine. If that was your approximation, you could pretty much stop there. If you want, now the last one was easier to get a common denominator. This one is definitely more problematic. Like, this would not be super fun to get a common denominator here. I mean, you certainly can. It's not the most fun thing in the world. You could do 108 divided by 6 and see what you need to multiply by. So this is going to have to be multiplied by 18. So you could do 108 times the, 108 over 108 times the 3, and you'd get a 324 over 108, minus apparently an 18 over 108, minus a 1 over 108. If you subtract 20, it'd be a 304, and I'm subtracting 19, so it's a 305. So I get 305 over 108, which I'd probably write as a decimal anyway, right? But we're assuming that you didn't have that option. So there you go. So we can see that that's what my approximation comes out to, but if I do the square root of 8, so if we do second root 8, you can see that's a pretty not awful approximation, right? So the actual value of this and the approximation are pretty close, which is yet another cool application of Taylor polynomials. All right, so Mclaren is just another name for a Taylor series, but centered at 0. So all of the ones we've done so far, oh, sorry, this should have a parenthesis around it, my bad. Okay, because it's the derivative, right? So, and this should also have a parenthesis, my bad. So, all of the things you've done so far, all of the ones that we've seen where we were centered around 0, they could also have been called Maclaurin. So for Maclaurin, you don't have to say Maclaurin centered around x equals 0. Maclaurin implies that it is a Taylor series specifically centered where x is 0. That's about it. So there are several Maclaurin series that come up so often, like so often, that you absolutely would be nuts not to memorize them. So while it is possible to figure them out from scratch, and we've done some of them earlier in this video, it is a terrible, terrible idea. So please commit to memorizing a handful of these Taylor polynomials centered at 0, but we can also call them Maclaurin polynomials or Maclaurin series. Okay, so we're going to quickly make the Maclaurin series for sine x from scratch, right? And then once we have the series from scratch, we should never have to do it again because I want you to memorize it, okay? So we're going to walk through how to make the Maclaurin series for sine from scratch, right? So if f of x is sine, we've kind of done this a little bit already. F prime of x is cosine. F double prime of x is negative sine. F triple prime of x is negative cosine, yeah. And then the fourth derivative loops back to the beginning. So it's sine, but I want you to notice that it looped back to the beginning, right? Like it's a loop. It's a loop. Okay, so if we evaluate at 0, because it's a Maclaurin series, which is when x is 0, right? F of 0 is 0, f prime of 0 is 1, f double prime of 0 is the sine of 0 again, which is 0, f triple prime of 0 is a negative 1, and then f with the fourth derivative loops back to the same spot. And again, it's a loop, right? So what's going to happen is that sine of x, and you can spot this pattern pretty quickly in a second, but sine of x is going to be the first term's gone, right? It's a 0. And then it's going to be a 1 times x minus 0, right? Next term's gone, no squared term, right, because the 0. And then a negative 1, x cubed over that 3 factorial, right, because there's going to be, the third term has a 3 factorial. Then the fourth term's going to be gone. Well, this is a loop, so it's just going to keep looping. So there's going to be a 0, and then it's going to loop back to the 1, right? Like this is the same spot. Like these two are the same spot in the loop, right? So what's going to happen is we're going to get a 1 times the x to the 5th over 5. There's not going to be a 6th term because you see how all of these powers, you see how all of the even derivatives are gone. And then we're going to get a negative 1 and x to the 7th over 7 factorial. So basically what happens is we can figure out that the sine of x function, so it's approximate if you don't have all of them, right? But it's actually equal to if you put the infinite sum, right, starting essentially at n is, we'll start at 0 and go to infinity, of all of the odd powers, right? So the odd powers, the way we write that is 2n plus 1. So this will be the 2n plus 1th. Oh, we don't even need that. Sorry, I don't need that derivative. It's going to be alternating, so it's going to be a negative 1 to the n, because it starts positive, x to the odd powers. The way we write odd power is 2n plus 1 over a 2n plus 1 factorial, because that's the way we write odd. So just as a hint, right, the way we write an even power is 2n, right? And the way we write an odd number is either 2n plus 1 or 2n minus 1. That's how you write that something's odd. So sine is going to be the sum of an x and then negative x cubed over 3 factorial, positive x to the 5th over 5 factorial, negative x to the 7th over 7 factorial. So it is not an accident that sine is an odd function, right? This is an odd function if we go back to thinking about even and odd functions, and it has all the odd x to a power over whatever the power is factorial, right? It's got the odd ones. If you do the same thing with cosine, right, I want you to try it from scratch once, but then you should absolutely memorize it, right? So if f of x is cosine, right, f prime of x is sine, sorry, negative sine, my bad. That's a negative. F double prime of x would be negative cosine. F triple prime of x would be sine, right? And then it loops back, right? So the fourth derivative is going to loop back to here, right? That's what's going to happen. So f of 0 is going to be 1, f prime of 0 is 0, f double prime of 0 is going to be a negative 1, f triple prime of 0 is going to be a 0, and then it's going to loop back, right? The fourth derivative and so on. So what's going to happen is that your cosine is going to be the first term, right? And we'll say approximately until I write all of them, the first term. But then there won't be an x to the first value, right? Because like there's not an x to the first. And then a negative 1 over 2 factorial x to the second. And then there won't be an x to the third. But then there will be an x to the fourth. And then there won't be an x to the fifth, right, etc. So what's going to happen is the cosine of x can be written as the infinite sum, starting at n is 0 to infinity, of a negative 1 to the n, x to the 2n over 2n factorial. Cosine is an even function, so it's going to look like this. Oh, sorry, minus. Right? It's going to alternate signs. It's going to have all the even powers, dot, 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 dot. So it's not an accident that cosine is an even function, and it has all of the even powers, right? Where it's x to the power over the power factorial. See how it's all the evens? Because even this is an x to the 0, and 0 is an even number, right? So it's not an accident. All right. So we're going to go ahead and do two more real quick. And I know this has been a super long video, but it's because we've covered an awful lot of material. So we're going to reverse engineer the Maclaurin series for 1 over 1 minus x from scratch, but I'm going to give you a hint. This is actually a trick. Remember that the geometric series, right? So remember that the series, let me rephrase. Remember that the series a plus a times r plus a times r squared plus dot 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 a times r to the n, right, converges to a over 1 minus r for absolute value of r is less than 1. So if I wanted to write this thing as 1 over 1 minus x, what's interesting is if a were a 1, if a is 1 and r is x, this series would look like 1 plus 1 times x plus 1 times x squared plus dot 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 1 times x to the n, and it would converge to a over 1 minus r. So the trick is that this thing can be written as the sum from when n is 0 to infinity of a essentially just a 1 x to the n, or just x to the n. You don't even really need the 1 because you can just, so that's our Maclaurin series. But it comes from the geometric series, a little bit different than the way we reverse engineered the sine and cosine. You could try and figure this one out by actually doing all the derivatives, but you'd pretty quickly start to hate your life a considerable amount. Maybe not, I don't know, but it's not super fun. So, okay. Oh, if you wanted to do this the really ridiculous, awful way, right? The other way to do it is your f of x is 1 over 1 minus x, which is the same as a 1 minus x, the negative first, right? So f prime of x would be a negative times the quantity 1 minus x, the negative second, times the derivative of the negative x, which would look like this, right? And then your f double prime of x would be, so here this net's positive, right? These two together would net positive. So it would be a negative 2 times this thing to the negative third, but again times the negative 1. So again, they'd net positive, right? So you'd get a 2 over this thing. Third, right? And then if you kept going, right, you could keep doing this, right, forever. So then what that means is that f of 0 is just a 1. F prime of 0 is also a 1 over 1 squared, so it's a 1. F double prime of 0 is a 2 over 1, so it's a 2. Well, if you look at what this Taylor polynomial would look like, right, so this would be 1 over 1 minus x. This would end up being f of 0, right, plus f of 0 times x, or f prime of 0 times x, rather, plus f double prime of 0, which is 2 over a 2 factorial, which is conveniently another 1 times x squared. So you'd end up figuring out pretty quickly that it does look exactly like this, but it's a little easier to realize that it can also be a geometric series. All right, so last one, I want you to try and make the Maclaurin series for e to the x from scratch just the one time, and then you'll never have to do it again. So we do this the same way we did sine and cosine, okay? So f of x is e to the x, And then every single derivative is also e to the x, right? So all of the derivatives are just going to be e to the x, right? Which means that f of 0, which is e to the 0 or 1, that's going to be true for literally every derivative. They're all going to be 1. So like fn of 0 for all of them is going to be a 1. So my series is going to be 1, right? And then 1 times x minus 0, right? And then 1 times x minus 0 squared over a 2 factorial, right? And then 1 times x minus 0 to the third over a 3 factorial. And so what you're going to end up getting is an x to the n over n factorial. And that's it. So e to the x can be written as the sum from n is 0 to infinity of just an x to the n over n factorial. And again, we're going to want to memorize that. So here are some of the Taylor-Maclaurin series you want to remember. So these are the big three. It doesn't hurt to memorize others, but these three, sine, cosine, and e to the x, are 100,000,000% going to happen. They're going to come up on an AP. We did the 1 over 1 minus x down here, right? There's also one for inverse tangent, which, so in my brain, I always remember the inverse tangent one looks just like the sine, but without the factorials. Because if you look, it's an x and then an x cubed over 3, but instead of being 3 factorial, it's just a 3. So again, and I already gave these hints about remembering sine as an odd function and cosine as an even function, etc. There are a couple others on this next page, right? So this one is the same idea as the 1 over 1 minus x, except instead this is a geometric series where r is a negative x, so you'll see the sign alternates. Instead of being 1 plus x squared, it's 1 minus x plus x squared minus x cubed, etc. If you wanted the natural log of 1 minus x, this is actually what happens if you integrate the 1 over 1 minus x, and we'll learn how to do that in a later video. The same thing if you wanted the natural log of 1 plus x, that's actually what happens if you integrate this formula, if you integrate each piece, right? If you were to integrate 1, you'd get x. If you integrated a negative x, you'd get a negative x squared over 2. If you integrated the x squared, you'd get an x cubed over 3. And we're going to go into that in other videos because this has already been a pretty long video.